All right, so welcome to a midsummer INC IM neuroengineering seminar. So very delighted to have with us Chul Kim of KAIST, right? Korea Advanced Institute of Technology, Science Technology. Um, and Chul was here as a great star student in in bioengineering here in UC San Diego. Several years ago, received great awards, Usami Award, right? Has been since then a faculty member at KAIST, right, where he's now associate professor, has been doing exciting work at the interface between biomedical integrated circuits and systems and medicine. And so very delighted and to hear a great story. So please go for it.
Okay. Yeah. Thank you for nice introduction, Kurt. And then thank you for having me here. My name is Chol, and I'm very honored to speak over here today about the miniaturized neural engineering systems enabled by the low power, energy efficient integrated circuits. Uh, uh, Actually, today's talk, I will first convince you the why low power ICs is very important for the biomedical applications, and second, I want to introduce some important applications in which the low power IC plays an important role. But I realized that the most of the guys coming from the girls, so that the first topic, the convincing the why low power is important, is not very necessary. But let me anyway try to convince you. Okay. uh, okay. Before diving into my talk, let me first introduce our lab members. Without them, I cannot do anything for the research, and then or with their hectic effort, so we can achieve a lot of things. And we are now tackling the many challenges in biology, medicine, and neuroscience, utilizing the biomedical energy efficient electronics to implement invisible brain-machine interface. Invisible means here it doesn't need to be it's very small, tiny, so that it is unobtrusive. Okay, don't confuse with the invisibility clocks. Okay, in the Harry Potter. Oh, okay. Let me just. mm. Okay. So basically, we wanted to implement very small, tiny miniaturized neural engineering systems. But again, why do we need a low power integrated circuit for the biomedical applications? Let me show some the conventional, quite old brain machine interface applications. The first one is controlling wheelchair, and the second one is actually the controlling the robotic arms. Both are presented the 2010 and 2016 respectively. As you noticed, both devices are relying on the wired operations. As you can see, the electrode here, on top of the brain, they put the electrode here, and then the electronics such as amplifier and ADC located here. And then between two devices, they connected through wires. Because the amplifier and ADC is very huge, so that they cannot put this device on top of the brain. So they they utilize a separate space for the amplifier electronics, and that's why they have to they have to connect both devices through the wires. And here also the device utilizes wired operation. So as you noticed, as you imagine, a wired device is our big enemy. We have to remove wires, cause wires induce many problems, such as the increasing the thermal noise and induce the motion artifact. And even the easiest thing is actually it limit mobility of the subject, right? So we want to remove the wires. Then first we have to figure it out. Why do we have to use wires at the current system, right? So let me show some of the important building blocks for the brain-machine interface. The first one is, of course, the most important one is brain, right? So for the brain-machine interface, brain is the most important thing, of course. And then the electrode and amplifier and analog is a converter, and then the some computing machines, and then finally we need the target machines. But especially here, between electrode and amplifier and ADC, analog digital converter, they need to be connected through the wires. It is because, especially the electrode, they typically do not have any energy source. So for the wireless communication, in order to implement the wireless communication, we need what? We need some Bluetooth or Wi-Fi, something, right? That means we need energy to operate the wireless component, right? But the electrode, they don't have any energy source there. So between electrode and amplifier, we have to utilize wires. And then between amplifier and ADC, they are electronics. Electronics typically need energy, right? So that's why we every day we charging our cell phone, and I'm still charging my laptop because the electronics require energies always. So the power source should be connected to the amplifier and ADC through wires. So between electrode and amplifier and between the power source to the electronics, we always need wires, right? Then how can we remove these wires? It's impossible, to be honest. Removing wires is impossible. Then what is the best way to reduce the impact of wires? How can you implement a fully wireless system? In order to avoid, as an alternative, we might implement integrated system. We can put all stuff into one small miniature system, such as amplifier, electrode, and ADC. They are implemented on small, tiny devices. Then still we utilize wires between electrode and the amplifier, but the length of the wires can be minimized, right? So that every wires can be local, so that the impact of the wires can be minimized. This is the way to avoid or implement fully wireless brain machine interface systems. And then of course this device should be operated by batteries. What it means, okay, in that case, then after digitizations, we can deliver to the computing machine all data wirelessly, okay? But what I'm saying is actually these devices, amplifier and ADC, should be located on top of the brain. Okay, then the wires between the amplifier and the electrode, these lines can be minimized, and then it cannot be seen outside. Okay, so that's the way of implementing fully wireless systems. There are some such devices. At 2022, I believe this one is published by the Brown University, and they published they shows fully wireless brain machine interface systems. As you can see, they have two devices for the motor part, and this is sensory part, and then they put the two device system, and then with this device, they demonstrate the brain machine interface, the connections. But as you noticed here in this figure, still the fully wireless device is somewhat obtrusive, right? Somewhat bigger, so somewhat large, right? So although this is very advanced one compared to the previous brain machine interface system, still very large. Why? This device, the size of this device is actually limited by antenna located here, and the battery. Okay, the size of battery and antenna actually limit the size of the brain machine interface system. Then, okay, for the antenna, we will talk about that later. But for the battery, why do we have to use such a large battery? If we can utilize a small miniaturized battery, then the size of the brain machine interface system can be decreased, right? Then we can use the small one. There are so many small batteries, right? The coin battery or button cell battery. There are many, but they utilized very big one. It is because these electronics consume huge amount of power. So that's why they have to use a large battery. Then here, if we can somehow design low power electronics, then we can decrease the size of battery. Okay, here now you can just get the answer for this question, right? Now I believe you guys convinced that we need low power system for the miniaturized brain machine interface, right? There are many other reasons, but anyway, there is one of them. And um, so we have to design a low power biomedical IC for the neural engineering systems. So that's the connection between the neural engineering and the IC. Okay, from now on, I want to talk about the how to design the low power IC. Now, first of all, let me introduce some work that I did at UC San Diego. Like Gert introduced, I did my PhD in this school from 2012 to 2017, and then I did my deep PhD defense in this room. And then at the time, I believe it was quite successful or not, I don't know. But anyway, I did defense here, and then at the time I also presented this one. But let me present this one again. So uh, in order to record the brain signals or any biopotentials, we need amplifier and ADC because the biosignal is quite small. So that we need a large gain amplifier and then we amplify it. After that, we have to digitize it. However, that's this correct approach and that's good one. However, the problem is neural signal or biopotential always come with the artifact, such as stimulation artifact, motion artifact, or chewing artifact, a lot of artifact. And the problem is artifact is way bigger than neural signal or biopotential. Then the amplifier, typical amplifier has the maximum output voltage. If it depends on the design, but if amplifier utilizes 5 volt supply, then output voltage swing, maximum voltage swing range is typically limited by roughly 5 volt or 4.5 volt, something like that. And then if output voltage is limited, and then maximum input range is also limited, divided by gain. Output range is 5 volt, and then gain is 1000, then maximum input range would be 5 millivolt, right? So, and then maximum input range is also very limited. But if a small signal and along with a large artifact come with together, then amplifier can be saturated. And then depends on design. It needs long time for recovery from these saturations. And the problem is, if we received repetitive artifact, then this entire system becomes useless. That's why when I did my PhD with Gert, and we discussed a lot, and then we designed this system, ADC track front end. Okay. The problem is, what is the main problem of this chain? Main problem is large gain. It's strange, right? Amplifier needs large gain. Amplifier, what is the main purpose of amplifier? Amplification. But the amplification itself is big problem. Okay? Because of large gain, input voltage, input range is limited, right? Then why do we need a large gain? I said before, biosignal or neural signal is very small. That's why we need to amplification. Okay, small. What is small? Small is very subjective word. 10 volt is small? Minus 10 volt? Not minus, no, 10 microvolt? Or 1 nanovolt? Which one is small? Actually, small means very subjective word. Actually, neural signal is smaller than noise induced by ADC. Analog digital converter is strong noise source. It inherently produces quantization noise, thermal noise, and a lot of noise coming from the ADC. And neural signal is way smaller than the ADC noise. That's why we need to amplify biopotential signal to the larger than quantization noise of the ADC. Then what happens? If we can design low noise ADC, do we need amplifier? Actually not. That's why we proposed high dynamic range, low noise, extremely low noise, and low power ADC. And by doing so, we can eliminate the amplifier. Due to this method, we can reduce power consumption consumed by the amplifier. And we could design the area efficient design because we can eliminate amplifier, right? So this method is quite successful, and then we wanted to call this structure ADC direct front end. To be honest, I wanted to say the ADC first front end, but the girls want to ADC direct front end. So at the time we discussed a lot, but finally we decided to call it ADC direct front end. And yeah, anyway, it was amazing because we can eliminate the amplifier so that this structure can enjoy large input dynamic range and low power because of no amplification stage. Okay, with this system, we compare we compare to the most famous not most, I don't know, anyway one of the most famous the neural interface system design, which is Intan RHD. Compared to the Intan system, the ADC direct front end consumes can reduce the area of 50 times area reduction, and it achieved the 100 times power reduction, which means per channel power consumption is less than 1 microwatt, which is amazing. So that now we can design low power integrated circuit, and then low power integrated circuit. And then with this system, we tested this system with a small monkey called Marmoset at the UC San Diego, and then from the monkey, we can record the brain signal. And then as you noticed here, along with the large artifact, such as chewing artifact, whenever monkey try to eat some food, it produced the chewing artifact. But along with the chewing artifact, as you noticed, we can still record local field potential. Okay, so I said in conventional system with this large artifact, we cannot record anything. At the time, we record the brain signal simultaneously along with the Intan system, but that system cannot record any signal. And only our system can record local field potential along with the large string artifact. Okay, that's what I did during my PhD. Then after become professors, what can I do? So with my students, it's amazing. Okay, we designed large input dynamic range. Then what is the next job? Okay, think about it. This is the brain. And then we try to record biosignal, neural signal, which is very small again. And then we wanted to provide stimulation. Stimulator typically produce large stimulation artifact, such that the recorded signal is small brain signal along with large artifact. Basically, what it means, this artifact contaminate biosignal. Okay, and then now what we can do is currently, even though we have large artifact, doesn't matter because of our ADC direct front end can record everything, small signal and large signal all together. Then what's next? These data, this recorded signal will be delivered to the computing machine, and then running some algorithm such as ICA or PCA algorithm, and then this stimulation artifact will be separated and then removed. Because stimulation artifact is not real signal, and then pure biosignal will be recovered. That's the current process. But think about it. If large signal is here and then small signal here, which one is the real data? Which one is the real data? Small one is the real data, right? But then we can deliver only small data to the outside, but this contaminated signal should have large signal and then small signal all together. That means in order to achieve some resolution, we need to cover 22-bit to cover entire voltage range. But actual information will be just 8-bit. So the wireless communication, actually it can deliver only 8-bit, that's enough. However, because of this artifact, the fake signal, the wireless communication should deliver 22-bit, which consumes around 3 times more data. More data rate means more power. So what is the best way then? Why do we need to deliver this fake signal to the outside? if we can somehow handle this artifact in the hardware, then we don't need to deliver 22-bit. We can just simply deliver 8 bits, right? So we presented some the processing in sensor system, kind of the we designed the adaptive filter to sense the artifact only and then filtering out. So there is the design. Actually we at very first time we mimic the we bought the ADC and stimulator chip to produce recording biosignal along with the provide the stimulation, and then we put the FPGA here, and the FPGA learning some the adaptive filter, designing some learning some adaptive filter, and then with this system we tried to record some signal from the radant, and then as you see here, this is a recorded signal. This small one is actually real signal, is real brain signal, and then this large spike is actually stimulation artifact, because we provide 100 hertz stimulation. Okay, and then as you see, we cannot see anything except for the stimulation artifact, and this one is what? Is breathe. Okay, the radant is, even though the is breathe, and then this one is recorded for the channel 1, and at the channel 2, we record simultaneously. And then but channel 1, no algorithm, and channel 2 has algorithm. And then as you can see, at channel 2, we can clearly remove, we can clearly remove stimulation artifact, and that's why we can see clear spike signal, right? And then as you can see, this breath is still there. So this time, this one is the same thing. So we can recover stimulation spike signal, which was hidden by the stimulation artifact simultaneously. Wow, I believe that we make a great success. So that okay, why don't we now make this is too big system. So why don't you make a chip running the algorithm onto the digital system? So that we designed a wide input range ADC, 8-channel, and then here we designed the current stimulator, and then here we designed the data processing system that implement the adaptive filter. And then with this chip, we recently tested this chip, and this chip size is 2 square millimeter, and then we again recorded from the radant, and then at this time, we cannot record the action potential, but we can record local field potential. With stimulation artifact, you can still get capture stimulation artifact and along with the local field potential. But if we learn the algorithm, stimulation artifact was removed, and then we can clearly capture only local field potential. So now this work was submitted. This work actually we submitted to some journals, and then we are waiting their decisions. Hope that is going well. Okay, then what is the next one? I explained the ADC jack front end to eliminate the amplifier, and the second one I explained the hardware processing to eliminate the stimulation artifact such that we can reduce the data rate. The third one is what? Why don't we need a battery anyway? Can we utilize wireless power transmission schemes to eliminate battery entirely? Then we can minimize, or we can reduce the size of the brain-machine interface system, right? So we can eliminate battery itself entirely. That's our goal. Okay, then why don't you utilize, anyway, the electrons require some energy, right? So we can utilize wireless power transmission. To be honest, wireless power transmission is already very familiar with us. You guys utilize probably Apple Watch or Galaxy Watch. Probably most of you guys probably Galaxy Watch. I know Apple Watch probably here. But anyway, for the charging of this watch, we utilize wireless power transmission system already, right? We don't make a physical connections, right? Just put on top of the charger, then battery will be charged, right? There is a wireless power transmission system. But Apple Watch or Galaxy Watch, for the charging system is quite easy setup, relatively easy setup, because the distance between the charger and the watch is what? Less than 1 centimeter, right? But if we wanted to we want to utilize wireless power transmission to deliver power to the implantable device, we have to deliver energy uh, of some implantable device of 5 centimeter apart or 4 centimeter apart. Okay, so we have to cover long range distance. Here, long range means a few centimeter, but the current wireless power transmission technique is very limited for the operating range, typically less than 1 centimeter. Let me explain why. So this is the main principle of the wireless power transmissions. We utilize two coils, one coil for generating the magnetic flux. If we provide alternating current, then the primary coil produces alternating magnetic flux. And the second coil will capture this alternating magnetic flux. Then this second coil will induce electromotive force to reduce the fluctuation in magnetic flux. That's the main theory of the wireless power transmission. The electromotive force can be extracted to the DC voltage. That's the main concept, main theory of the wireless power transmissions. But rather than in order to improve the energy efficiency or in order to deliver the more power, we added capacitance here because the antenna, loop antenna is basically what? Inductor, right? So if we put the capacitor, the inductance will be resonance out. So the impedance will be minimized here and the impedance will be maximized here. So given some certain voltage, maximum current will flow at the TX side. And at the same time, given the same current, given same the magnetic flux, maximum voltage will be developed at the receiver side. That's the what we utilize to improve the efficiency. But even with this system, we can still deliver a few hundred milliwatt or a few tens of milliwatt within 1 centimeter distance. That's the almost maximum. But the 1 centimeter distance is okay because the cochlear implant, typically they need only 0.5 centimeter distance. But for the brain, we need cover 1.5 centimeter distance. And then for the electric sticker, which can implanted on our gut, then we need cover 7 centimeter or 5 centimeter. So we need deliver long distance. We need deliver large power to the long distance implantable devices. And how can you do that? The solution is we can utilize, rather than parallel resonance, we can utilize series resonance. Here, previously I said we typically utilize the capacitor here for enjoying the maximum impedance. But rather than this one, we intentionally utilize the series resonance such that we minimize impedance here. The main purpose of this one is actually we want to receive current rather than voltage. Current is information. That in that case, then voltage will be minimized here. That means we can deliver large energy from TX. You see what I'm saying? Previously, we utilized we intentionally maximize impedance such that such small current will produce large voltage. Then large voltage is good. However, because of that large voltage, the switches in here could be breakdown. It could be damaged so that we cannot deliver large energy. But if we utilize a series resonance, then voltage will be here. It's very small, a few tens of millivolts, such that we can utilize these switches in a safe fashion, okay? Such that we can deliver large energy. Then, hey, you said we have to design the low power IC, but you said we can deliver large energy. Large energy means high power consumption, right? Actually, it's not true because this secondary coil is secondary system. If they hold large current, good thing is this large current will reduce the TX current because it's magnetically coupled. So RX side has large current, then TX side should have small current. Then which one is typically consume more power? Actually TX, because TX typically has large current. So loss is what? I square R, right? I is way larger than the TX current is way larger than the current that of RX. So typically TX consume huge amount of energy, but because of this scheme, actually energy consumption is reduced, a lot reduced, and then we can deliver more energy. And then funny thing is this one. This is most funny thing. Actually, this is a little complicated system, complicated figure, complicated graph. This one tells the distance between two antenna, and this axis tells the frequency, and then z-axis tells the gain, which means basically how much energy we received from the at the RX side. Okay, and then we typically utilize just one frequency, 13.56 megahertz. And think about it. If two antenna is getting further, in distance of the two antenna is getting further, then what happens? Received energy should be reduced. That's the natural thing, right? But yeah, that's true at this side. If distance is the critical coupling point, the received energy is maximized, and then distance is increasing further, then received energy is significantly decreased, very rapidly decreased. However, the funny thing is at this side. See, if distance is getting closer, received energy will be decreased. So getting closer, lower energy. What a strange, right? It's closer, small energy, further, larger energy, right? This side is actually very strange area. It is because of magnetic coupling. Because RX has a lot of large current, then getting closer, then this current will affect the TX a lot. So the TX current will be decreased. That's why we cannot deliver large energy. But if distance is getting further, then the coupling impact between the RX and TX will be reduced, such that it will recover its own current, such that we can deliver more energy. That's the main mechanism, okay? So by having the series resonance, we can deliver, okay, that is the main mechanism. And then as you can see, this was the sharpness at this area is very sharp, right? But this area is quite smooth. Then which one is better? Actually, this side is way better when we considering distance variation. Here, even if distance varies, but the energy will be variation in energy, received energy will be a lot reduced, right? So we can design robust system here against distance variation. So we intentionally utilize this area. And then with this scheme, we can implement watt power transmission system that can deliver over than 100 milliwatt at 18.5 centimeter distance. 18.5 centimeter distance. We can cover entire biomedical application probably if we can cover 18.5 centimeter distance. This system working from 3 centimeter to 18.5 centimeter. You can cover almost all biomedical applications. That's amazing. So we believe that, wow, it's everything done. You know what? The secret is actually antenna size is very big. As you can see, the antenna is 15 centimeter, TX antenna 15 centimeter, and then receiver antenna size is what? 8 centimeter and then 5 centimeter. It's huge, right? We cannot utilize this big size of antenna for the implantable devices, right? Actually, this application is for the smart card. Actually, I supported by Samsung, and they want to design I don't know whether they are working on now, but now and they started this project or not. But anyway, they want to implement a smart card. So for the application, we need this size of antenna. They actually give the antenna size, but with the exact same scheme, we again designed a new antenna and the new chips. The antenna size now is 3 centimeter. Okay, here 3 centimeter, and then at the center we designed 1 millimeter by 1 millimeter chip, and this system will be covered by PDMS, and then we implant this system on the stomach of the mouse, the experimental subject. And then we also utilize the exact same size TX at outside. We deliver energy to this system. And then this system will receive more than 100 milliwatts at 4.5 centimeter distance. And then even with this single two antenna system, we can deliver power as well as data. And then this device shows that they decoded data. Data rate is more than 1 megabps. Okay, that technology can deliver power from the skin to the inside of our body or inside of our animal, right? Then how can we deliver from external source to the skin? Because the power is located where? Probably wall code. We have wall code, right? So from the external, we have to deliver energy to the skin, and then skin to the implantable device. We can use the previous scheme, but how can you deliver energy from external to the skin? Okay, for this purpose, we design this smart cage, which can utilize the capacitive coupling. So for this one, we also utilize magnetic coupling, right? We put the two antenna. So one antenna is holding by this animal, and this side, this cage also have one antenna. Then we can deliver energy wirelessly, right? With the exact same scheme. However, the problem of the magnetic coupling require alignment. If two antenna is misaligned, then no energy will be delivered, or energy the amount of energy delivered to the RX antenna will be significantly decreased. So the freely moving animal cannot receive any energy. However, we intentionally utilize capacitive coupling. What's the capacitive coupling? If we utilize capacitive coupling, then the capacitive field, E field, will be spread out, right? And then there is fringing field. We intentionally utilize the fringing field. So even if these animals will be fully moving or misaligned, doesn't matter. Fringing field will be everywhere, spread out everywhere. So this is simulation result. If we utilize inductive coupling, then only this spot we can receive much energy, but this side energy consumption, received energy will be significantly decreased. Depends on location. We cannot receive any energy, and then depends on height. If they are moving up, then distance will be close together, so that we receive a lot of energy. So depends on distance, energy will be decreased, changed a lot. But if we utilize a capacitive coupling, regardless of the position, regardless of the posture, doesn't matter. We can deliver energy of very flat size. No energy variation, or almost zero energy variation. So we utilize this smart cage utilizing capacitive coupling, and then we can deliver energy here. See, these animals, there is no wired connection between this smart cage and the animals. And then they are, as you can see, this LED, right? We deliver energy to the animals, and animal receive energy and then turning on the LED. Okay. And my ultimate goal is actually what I want to design is actually this one. This work was also done with the GERT when I did my PhD. And then we try to implement some small chip, brain-machine interface on chip, or neural-machine interface on chip, which means we integrate all required components for neural interface, such as electrode or antenna or the stimulator, everything every important or every component for the neural interface we integrate onto the chip. That's what we want to do. Then small tiny system becomes brain-machine interface system. That's our ultimate goal. However, that one is quite difficult, and then we did a great job, and we also achieved good result. However, I wanted to design this system again with my students again. So this is my ultimate goal, and then we are heading there actually. And then let me simply introduce some wearable devices. Okay, so there are many wearable devices, especially for the ECG. You probably know about the ECG, right? The heart activity. And then what is the typical method to measure ECG signals? Typically go hospital, right? And then we utilize the wired ECG at hospital, right? This is the typical way. And then these days, someone presented or some researcher developed wearable ECG devices, which are looking relatively good, but anyway, and it works pretty well. However, still, I don't think this one is actually what I did actually still in the UC San Diego. But anyway, this one is looking relatively good, but I want to go further. What is the next wearable system? I believe wearable system is quite uncomfortable because it's quite large and obtrusive. So it's not easy to handle in normal life. So what is the best way to capture biopotential using wearable system? I believe we have to put the wearable system in the our normal life setup. What it means? It should be in the bed. It should be in the chair. It should be in the car. It should be in the anything in our normal life. So we first integrated the system into the bed. In the bed, underneath of the mattress, we put the electrode and the amplifier there. And then actually this, we borrowed the Garth's idea. Garth is really good at the non-contact sensing scheme. And he, just before, he actually explained the main idea of that one. And then we also borrowed that non-contact sensing scheme here. And then this sensor will be located underneath of the mattress. So it cannot be visible at outside, just normal bed, okay? But if the subject is lying down on the bed, then ECG signal will be captured automatically. And then the captured signal will be processed by the FPGA system. We designed wavelet transform. Wavelet transform is really good for the denoising because the wavelet transform is what? It's basically we utilize some basis which is very similar as the ECG QRS peak, and then we capture QRS peak only, and then remove the all noise component, and then recovery. Then we basically separate the signal component and then remove the noise and then recovery, so that we can increase SNR basically, okay, by doing the method. So with the FPGA, we developed a wavelet transform here, and then as a result, actually this project was supported by the Seragem, which is the massage. They generate the massage bed, and they wanted to integrate the ECG sensing system underneath of their system. So this is Seragem, the massage bed, actually version 4, I believe. And then we put the ECG sensor underneath of this Seragem bed. And then this one is a DRL, it's active electrode. And then here there are two sensors. And then as you can see, the subject wears just normal the clothes. Even with this system, we can see we can capture the ECG signal. Okay, it's working, right? It's video is working. And then this one is the DRL, and then here we put the two electrode, and then see ECG signal captured simultaneously. And then we have computer and the monitor, but there is just display machine. We do not anything on the device. Everything is happened in the on the FPGA side, FPGA hardware side. And with this system, because of their own device processing, very interestingly, even with some artifact, this is motion artifact. Think about it. When you sleep, then we have to moving around, right? Even with a certain level of motion artifact, we can still capture QRS peak correctly. But at the large artifact happens, then QRS peak cannot be captured anyway. So we are now developing new idea to tackle these problems. But anyway, at a certain level of motion artifact, we can capture R peaks very well. And then think about it. Someone says, "Oh, my clothes is very thin," but someone says, "Oh, I love to wear the parka or the winter jacket at the bed." No one do that probably, right? But anyway, just in case, someone probably wear this kind of thick clothes on the bed. I don't know whether, but anyway, even with this thick clothes, we can still capture some signal. This is very noisy one. But funny thing is here, still the on-device processing can capture R peak very well. So this short, we can capture very clean ECG waveform. And this one, we can still somehow the wavelet transform, denoise the noise signal. And the yellow signal is denoise one, which is quite okay. And this size, the yellow one is still quite noisy, but we can still capture the R peak very well. And then even this one, we can capture, actually the yellow one is very noisy. We cannot see anything. However, still the FPJ will capture R peak very well. And now actually this one was is now we want to design the wearable sensors on the abdominal ECG sensors. For the pregnant woman, they wanted to capture the baby ECG signal. Current method is what? We utilize ultrasound. But the ultrasound, we believe is safe, but actually FDA do not recommend to utilize ultrasound to the baby many often, because anyway, what is the basic mechanism to capture ECG waveform from the baby? Actually, we deliver energy to the baby inside the womb, and then we receive the returned energy, right? Which means we give energy to the baby. So the FDA do not allow to utilize that kind of technique for 24 hours. It's impossible. It's not safe at all. So nowadays we wanted to monitor the fetal ECG utilizing ECG sensors. Okay. But the problem is what? If we put the wearable sensor on top of the abdominal here, the problem is mother ECG is also coming together. So we should record the signal simultaneously. But the main goal is what? We want to only record the fetal ECG only, right? So we designed the FPGA system that can separate the mother ECG and fetal ECG simultaneously. So with this sensing system, we can capture we design relatively well. Okay, let me anyway, I have some time. Let me explain this one. So this black one is what? This one is this small one is fetal ECG, and this large one is mother ECG. Fetal ECG is way smaller than mother ECG, and then the blue one is separated the mother ECG, and the red one is separated fetal ECG. But as you can see, even if separated, we can still capture some mother ECG here, right? And then with this mother ECG reference, we can remove this mother ECG term. And then we utilize a nonlinear energy operator, which is good for detecting the spike. And then with this system, we can capture fetal ECG only. See here, fetal ECG captured, fetal ECG captured, fetal ECG captured, right? So we can capture fetal ECG only. So this one is submitted to the biocast, and then hope that we are waiting the result. Hope that we can receive a good result. Okay, so at the very first time, I explained that the fully wireless brain machine interface system. The solution is we can integrate all required components into the small system. Then it can be fully wireless. Then what is next? I wanted to remove this computer somehow. I want to remove this computer. We don't need a computer anyway. Then if we can design integrated neural recording processor, then we can eliminate even computer. So that's our way to go. And then we hope that we can achieve some result out of it. Thank you.
Questions, both here in the room or over Zoom? Yes, please.
Hi, great presentation. So I have some questions about like the first device you showed where you can analyze the local field potential, but could not do action potential. Was that limited by this SNR or if because like the SNR even for your local field potential was like not great. And then was like the resolution in terms of time because the action potential has a different time as compared to the local field potential.
Okay, I see.
The limitation and like how you're like improving those.
Okay, very good question. Actually, she actually asked about the simulation artifact removal system, and then at the FPGA. Oh, let me go to the slide actually. This one, right? Actually, at very first time, we can capture spike signal here at the FPGA system. Along with the FPGA system, we can capture spike. But with the chip, we cannot detect action potential. We only record local field potential. Then she asked, what is the main reason? Is it because coming from the bandwidth or coming from some other issue? Actually, that is coming from the electrode issue. And then with this electrode, we provide no stimulation at all, but still we cannot capture action potential at the time. So and then the best way is actually we try to do it one more time, but the in vivo test is not an easy job, right? And then we cannot sacrifice anyone so many times. So we just decide to use this data as is. So without stimulation, we cannot receive any action potential. Only local field potential. So I believe the location or noise issue, but actually we measure noise, and noise is good enough to capture the action potential. So I believe anyway the environmental noise, biological noise, or the electrode itself may be very far from the neuron. So if we have multiple animals and we can sacrifice everything, then we can do that. But actually we decide not to do that. Yeah.
I'm an undergrad, so I don't know much, but I was wondering if you can break the sine waves into individual sine waves on total, like using Fourier transform or something. Is that possible?
You mean this one? Your question again, please.
Well, like if you have one sine wave, can you break it into individual sine waves based on like amplitude?
Very good question. Very smart. Yeah. Actually, I haven't tried, but I think it's a good approach, I believe. But I think in order to separate separation, probably consume more power, I believe. But anyway, that's good try. Let me think later. But I haven't think about it. That's good try. Yeah.
So for the mother and the fetus ECG recordings, where exactly were the electrodes placed?
So his question is actually this one. So for mother ECG and fetal ECG, where is the ECG electrode located, right? So actually electrode is around here, abdominal, this side. But ECG is very strong signal. Probably the Gulf Lab actually recently designed the in-ear EEG. Even here, you can record ECG signal. So ECG is everywhere in the body. So here, we can still capture ECG, mother ECG signal and fetal ECG together.
But how many electrodes are there?
How many electrodes?
And where are they placed?
We utilize 3 electrodes, 2 signal, and one is for the ground, the active ground. Yes.
So then we're removing the mother's signals from the signals we get from both, and the remaining signals, that's what the fetal signals are?
Oh, sorry, once again, please.
So we have a main signal that comes from the electrodes,
Uh-huh.
and then we get separate mother signals from another electrode, and then we're seeing the difference, and that difference is the field.
Oh, I see. Oh no, actually, the feral ECG and mother ECG has different characteristics. The mother ECG is slower, somewhat slower, and fetal ECG way faster. So typically, our ECG is what the 16 times or 70 times per minute, but for fetal ECG, typically 170, 130 to 180. So somewhat different characteristic. And actually, we utilize only two electrodes, but we utilize the differential recording, right? Differential recording means actually, and then basically it's one channel. For one channel recording, output of the one channel recording signal, we have two signals, two signals. One is for this signal is we recorded combined signal, mother ECG and fetal ECG, and then with the characteristic we can separate them. Yeah. No, not only for the characteristic. Actually, there are many other schemes, but anyway, what I said is mother ECG and fetal ECG is somewhat different. So with the characteristic we can separate them.
In fact, that question relates to the original withdrawal and formalization, right, of how to adaptively process a weak signal, right, to remove the strong signal. So if one of the electrodes is placed close to the mother's heart, that would pick up mother's heart signal, and that can then be adaptively right removed, right.
Very creative idea. Yeah. Yes, very creative idea.
Hello.
There's a question for Abraham. Yes.
Yeah, Abraham, please.
Hey, Chul, you know what this reminds me of? You could, I mean, right now you're doing a great job of catching the heart rate of the infant, right? Which is the most important part of the fetal ECG signal. But if you had more electrodes, you could classic the fetal signal out, right? This brings you some good memories, right?
Yeah, very correct. Actually, yeah, that's correct. And then, yes.
What does classic stand for, Abraham?
I don't know. I wasn't on the project. You are the PI.
Yes, I understand what you're saying. Very, very creative method. Yes, correct. Yeah, please.
I really think that field, so my question might be very fundamental.
No worries.
For your massage chair, a few slides back. I remember you mentioned that essentially as the person moves, you got noise signals to your recording system. My question is, maybe you've tried this already. Like, have you tried like just filter, I don't know, say like frequency filtering to get, because I assume that ECG would be at a specific frequency, so you could pick out that signal from noise.
I see.
Yeah. If you tried that or no, or there's
Oh, no, yeah, actually we tried, and a very, very good question. I mean, her question is actually for the motion artifact. We can utilize some filters such that we can reduce the motion artifact significantly, and then we can capture ECG signal very well. That's her question, right? Is that correct? Okay. Actually, we tried, but the problem is actually the ECG is very strange characteristic in frequency domain. Actually, if you see the ECG, it has the 10 to 40 hertz is a spike in the frequency range, which means it's relatively high frequency. So if we filtering out, this motion artifact will be removed. However, ECG QRS peak is also decreased. So noise will also decrease, but the signal itself is also decreased. And which one is bigger? Relatively same. So not easy to decide the best correct frequency, cutoff frequency. And then depends on the person, the ECG waveform, finding the correct cutoff frequency is not an easy job. So we intentionally utilize wavelet transform, which is time domain method rather than the spatial domain method. So time domain method utilize the wavelet transform utilize some basis very similar to the ECG QRS complex. So that in time domain we can try to capture this kind of waveform. using the wearable transform. And then that's why we can still capture some signal here, but we cannot. But again, if we utilize the frequency domain filter, signal is also decreased. That's my main message.
Because also, if you want to capture arrhythmias, then it's important to not rely on knowledge about a certain periodicity of the signal.
Yeah, correct, very correct. So arrhythmia is actually the yes, very important one actually.
More questions here. There's several people over Zoom too. Not so. Thank you very much.
Thank you, everyone.
Thanks for coming.
Thank you for coming.
In the middle of the summer.
Bye. Thank you, everyone.